Section 8.5, Polar Equations and Graphs. Now looking at this illustration to the left here, this is the first thing I want to talk about. So this point here is called the pole. And this line coming out from here is what we call the polar axis. Now that polar axis is where we actually start when we talk about graphing any angle. So what I mean by that is, take a look at the illustration to the right now. Now if I put this polar axis on this graph to the right, we get polar axis on the grid. So now when I look at this, we've dealt with the idea of unit circle idea, and we know that when I go in this direction, it's positive, and when I go in this direction, it's negative. So we're still dealing with those same components here, but now we're actually going to be talking about graphing points in polar. So now, for instance, if I had, let's say, a line here. Not a line, let's say a point. And let's say we're talking about this angle here. So that angle there would be theta. And then we would think about drawing the terminal side of that angle. And we can see that that theta is 45 degrees from here. So then if I drew these sides and created a triangle here. And also, let's say every 4 is 1. So 1, 2, 3, 4. So that'll be 1 there. So that'll be 1. So what I want to do is I just want to create that triangle. Okay, so let's put the sides in. So I drop this down here, and I drop this over here. Try to make it a little straighter. There it is. Okay, now we can talk about the idea of the sides of this triangle, and also what we have here is we have a radius here. Okay, we have our theta there, and this is our y value, and this is our x value. And honestly, from here, this is where all of those formulas come from. When we talk about the idea of converting from polar to rectangular, rectangular to polar. Now what I mean by that is, notice this angle theta here. If I wanted to say the sine of theta, okay, then I would write the sine of theta equals opposite over hypotenuse. Okay, now if I look at that triangle there, the opposite would be y. And the adjacent, the hypotenuse would be r. Okay, so then what I would have here is, if I actually solve for y, is I would actually have y equals r sine of theta. Now similarly, I can just do the other trig function too, the cosine function. So then if I do the other function now, the other function is going to be cosine. So I could say the cosine of theta equals adjacent over hypotenuse, and that would equal x over r. And again, there's my adjacent side, there's my hypotenuse. So then if I solve for for x, I would get x equals r cosine theta. So with these two equations, I can convert from polar to rectangular. Now we're thinking about this another way. Let's kind of go the other way with this now. So the idea of the Pythagorean theorem here, I would have x squared plus y squared equals r squared, correct? So then that would mean here that I get the equation x squared plus y squared equals r squared. So that's another equation that we have. And could I say something about the tan of theta? I could say the tan of theta, equals opposite over adjacent, so that would be y over x. So these are our 4 equations that we actually use to convert from polar to rectangular and rectangular to polar. So those are the ones that we got to get used to. So again, we can derive all those from just looking at a triangle in this space. So that's what's kind of nice about these formulas. And now you're going to have to memorize these formulas, or you should memorize these formulas, I should say, because you're going to use these all the way through all the calcs, and you're going to use them so much, it's good to be comfortable with these formulas. So anyways, that's our setup for those, and this is going to kind of give us the groundwork for most of the stuff we're going to do here. Just the idea of dealing with these equations. Okay, so now let's think about this point here. Now, if I was looking at this point, and that means this would be 1 up here, then my x and y is 1 if I look at this thing. So this is actually the point 1, 1. Okay, so now the idea here, this would be considered rectangular. Now, if we think about this point in terms of polar, we would have to consider here, I have an r and a theta, and that's what we're going to talk about now. We have these equations, and when I talk about points in polar, it's r and theta. So now, if I was thinking about this same point over here, the 1, 1, in terms of polar, I would have to know what r is. Okay, so right away I know that my x equals 1 and my y equals 1 if these lengths are both 1. So then that would tell me that I could find that r. So to find the r, I would use the Pythagorean Theorem, which is just here. So then I would say 1 squared plus 1 squared equals r squared. And 1 squared plus 1 squared is actually 2, so 2 equals r squared. So r equals square root of 2. Now be careful when you square root, because when we square root, we actually get a plus and minus here. But since we're just talking about a side of a triangle right now, we're going to just keep the positive. Okay, so that's why we see what we see down there, the r equals square root of 2. So that tells me here that this distance here, is actually going to be square root of 2. So now if I was going to write my ordered pair in polar, polar would be my radius, since we have this r theta here. My radius then is going to be square root of 2. And my theta is going to be 45 degrees. So this here would be polar. So one thing to notice here, that when I change from polar to rectangular and rectangular to polar, the graph itself doesn't change. The only thing that really changes here is just the coordinate pairs I use. But the point is still in the same spot. So that's what's really interesting about this. A lot of times when we do this conversion, we think that this point goes somewhere else, but it doesn't. It stays right where it's at. So that's a benefit of understanding that. Now there's another idea that we need to talk about here. We need to talk about graphing these points in polar. So now I'm going to use a different color here. So now let's say I wanted to graph the point, and I'll call it A, and I'll say it's 5 pi thirds. Oops. What am I supposed to put first? The radius. So let me put 2. Actually, I'll keep it about, every one, I'll go 2 for this one. I got to be careful because my graph only goes 2 out completely. So I got to stay within 2 for that reason. So I'll call it 5 pi thirds. Okay, now what I do first, I don't really change anything I've done when I think about this angle 5 pi thirds. So what I mean by that is, if I went all the way around here, that would be pi. Now, if I keep going, 5 pi thirds is going to be just before 6 pi thirds. So that should leave me pi thirds short. So it'd be here, I think. Nope, too far. So that would be here. So for instance, if I went all the way around, that would be 360 degrees. Pi thirds is 60 degrees, so it'll be 60 degrees short from going around once. So that's where my line would be. So now that means my line is kind of running, it's running this way, not kind of, it's running this way in that direction. And it says it's going to go in that direction too. So my point is actually going to be here, because I'm going out 2. And remember, this is 1, and so 2 is way out here. So just remember, I'm not using each little notch as a number 1. I'm saying every 4 notches is 1. So that would be 2 pi thirds. Now, what's interesting about this method of graphing, and the reason why I bring this up that's a little bit more interesting here, is that let's say I pick point B, and I say, hey, I'm going to go -1 pi fourths. So then that means I'm going to go up to pi fourths, and that's already labeled here, so that's here, and there's my 45 degrees. And since it's negative, well, if it was positive, I would run in this direction, and my point would be right there exactly. But since this is negative, I'm going to run in the other direction. Let me make sure I'm on the right one. Oops, I drove down the wrong line there. It would be this line out 1. Now, I think I went a little too far. Those 4 notches are getting me a little bit, so I'll drive a little slower. So there's 1, 2, 3, 4. So there it is. So my point would be there. So now, not all that other information is not necessary on my graph. Honestly, with any ordered pair, whether it be polar or rectangular, the result isn't any of that stuff. It's really just the point. So kind of keep that in mind too. I just drew that all in there so you can actually see where it's all coming from and actually where we're ending up and why we're ending where we end. If I just spoke about it, it might be difficult. Sometimes it's nice to see it. So this would actually be that point. Oops. B. That's kind of a weird thing for people to understand, that I can have a negative radius now. When I'm graphing, I definitely can. And I could write points in different ways. Polar points. Now, when I'm talking about points in rectangular form, when I get 1, 1, it's only 1, 1, right? But in polar, I can write that same point another way. So if I wanted to write B another way, I could say B is 1, 5 pi fourths. Now I'd go around. Oops. I'm going to erase this for a second. Hang on. And then that means I would go all the way around to 5 pi fourths. So 4 pi fourths would be here. That's at pi. Then I go a pi fourths more. That's going to put me here. Okay, so then my 1 is positive, so I'm going out in this direction, and my point ends up here. So again, we see that we get exactly the same point by writing in polar 2 different ways. So that's what's interesting about this method too. There's many ways I could write the point 1, 5 pi fourths. And the reason why is because I can keep going around in circles if I want to. I could use a much larger angle than that, so that's kind of the idea. So anyways, there it is. So we learned how to graph here. We learned about the equations from graphing from polar to rectangular, rectangular to polar. And we also talked about how points don't move, how they stay in the same place, whether I'm in polar or rectangular. Now the thing is I put this on a different graph, didn't I? And the way I always look at this, even when I was dealing with the unit circle, is I always look at it this way. And that this is my x-axis and this is my y-axis. So just kind of keep that in mind when I'm graphing. That's what I'm looking for. And that's why I introduced the x and the y early on that way. And that's how we generally look at it. It's like we place these 2 grids, like the polar grid, on top of the rectangular grid. And then that's kind of our mapping in a sense. So that's how it works. So we'll do some more in the next video, some more of these conversions and stuff. Here I was just getting a gist of everything. All right, done.